So this video is on how different elements react. Using what we learned about electron orbitals, periodic trends, we can actually understand how different elements react. We should be able to predict how different elements react. What I want you to be able to do after watching this video is understand the elements in a column behave alike because they have the same valence electron configuration. Understand that the noble gas configuration is extra stable because they have all full subshells, and so elements tend to gain, lose, or share electrons to get the noble gas configuration. And I want you to be able to use the periodic trends to predict which element of each group is the most reactive in general. And so valence electrons are the outer shell electrons, and they dominate chemical behavior. And so here we have electron configuration for germanium. And so outer shell, biggest N. And so germanium has 4 valence electrons. We'd say its valence electron configuration was 4s2, 4p2. Now notice that the D electrons are never ever going to be valence electrons because you'll only have D if you already have 4s. And so 4 is bigger than 3, and so the 4s will be the valence electrons. So D and F electrons are never valence electrons. Also notice the column, if you look at the column number, ignoring the transition metals, that will give you the number of valence electrons. And so the first column has 1 valence electron, second column 2. The column with boron 3, 4, 5, 6, 7, 8. The noble gases have 8 except for helium, which has 2. The halogens have 7 valence electrons. Hydrogen has 1 valence electron. Elements in a column tend to behave alike because they have the same valence electron configuration. Now that's not necessarily true for these middle columns that we'll talk about in a minute. So the alkali metals tend to form +1 ions because if they lose 1 electron, that will give them noble gas configuration. The alkaline earths tend to lose 2 electrons to get noble gas configuration, and so they tend to form +2 ions. Now I mentioned these columns, they don't really behave as well down a column because you can have nonmetals on top, so oxygen, sulfur, and nonmetal, and polonium is a metalloid, and so you shouldn't expect a nonmetal and a metalloid to behave alike. Or if you look at boron, here is a nonmetal, and then thallium is a metal. And so for these 4 columns, they really don't behave too similarly. Halogens, if they gain 1 electron, they get noble gas configuration, and so they tend to form -1 ions. Noble gases, again, they're extra stable because they have full subshells, and so they're not very reactive. There are some known compounds with argon, krypton, and xenon. There are no known compounds with helium or neon. But again, elements tend to gain, lose, or share electrons to get noble gas configuration, and we refer to that as the octet rule. And so we talked about the ionization energies, the energy required to remove an electron from an atom or ion in a gas phase. And if you remember, as you go up and to the right, ionization energy increases, so the metals tend to have lower ionization energy. That's why the metals tend to form positive ions. Electron affinity is the energy released when an atom or ion in the gas phase gains electron. And so as you go up and to the right on the periodic table, electron affinity increases. And so fluorine wants to gain an electron, and so the nonmetals tend to react by gaining electrons, forming negative ions. And so if we combine these trends, we see that, again, alkali metals form +1 ions, alkaline earths +2, halogens -1, oxygen, sulfur -2, aluminum +3. Now, I'm not going to expect you to remember the transition metals, and so these are the ions I expect you to remember what their charge is. So a type of question that you might expect would be, which of the following correctly lists the atoms and ions in order of increasing ionization energy? Now please remember that we treat atoms a little bit differently than we do ions. And so for atoms, we can just use the periodic trends. And so that first list is just of atoms. Now, if we look at the periodic table, we have oxygen, phosphorus, and francium. And as you go up and to the right, ionization energy increases. And so in that list, oxygen should have the highest ionization energy, and francium should have the lowest ionization energy. But it's written backwards. And so II is wrong. Now for the next one, we have calcium 2+, calcium plus, and calcium. Now calcium is atomic number 20, and so all these have 20 protons. Now the number of electrons for the neutral one is also 20. The plus one means that it lost 1 electron, so that would be 19. And the plus 2 means it lost 2 electrons, and so that would be 18. And so the top number is the protons, the bottom number is electrons. And so more electrons means more shielding, means weaker interaction. And so the calcium plus 2 should have the strongest ionization energy, and so II is also incorrect. And now we got F minus, neon, and sodium plus. And so we do the same thing in terms of protons. So fluorine's going to have 9, neon 10, and sodium 11. And so in terms of electrons, ion would have 10, neon 10, and then the sodium plus one means it lost 1 electron. And so the sodium ion would have also 10 electrons. And so that's an isoelectronic series, meaning it's have the same number of electrons. And so the more protons would give you the stronger interaction, higher ionization energy. And so the sodium plus should have the highest ionization energy, and the fluoride ion, the fewest number of protons, would have the lowest ionization energy. And so III is listed it correctly. And so if we look at another question, so this one, which of the following lists atoms, ions in order of increasing radius? And again, we can do the first one in terms of the periodic trends. So we have molybdenum, yttrium, and francium. So francium, yttrium, and molybdenum. Okay, and so as you go up and to the right, the strength electrostatic attraction between outer electron and nucleus increases, and so the size decreases. And so as you go up and to the right, the atoms get smaller. And so of this series, francium should be the largest, molybdenum should be the smallest. And so that one is correct. Now for the oxygen, that's element number 8. So you got O2 minus, O minus, O. So they all have 8 protons. And so the one without the charge has 8 electrons. The minus 1 charge means has 1 extra electron, so that would be 9 electrons. 2 minus charge is 2 extra electrons, so that would be 10 electrons. And so same number of protons, that's on top. More electrons, more shielding, bigger. And so O2 minus should be the largest, and O should be the smallest. And so II is wrong. And then we got calcium, 2 plus, potassium, and then the sulfur. And so sulfur has 16 protons, potassium 19, and then calcium 20. So the top is protons. Then in terms of electrons, the calcium ion would be 18. Potassium, 19 protons, that has a plus 1 charge. That's 18 electrons. And then the sulfur would also have 18. And so it's isoelectronic, same number of electrons. And so the more protons would lead to smaller, more stronger attraction leads to smaller. And so the calcium 2 plus should be the smallest of these, and the sulfur 2 minus should be the largest. And so the answer would be C, 1 and 3. So what is electron configuration of the most common ion that bromine forms? And so bromine is Br, it's right here. Now remember, if the halogens gain 1 electron, they get noble gas configuration. And so it'll get the noble gas configuration of krypton. And so we could go 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, and then 4p6. And then so for the ion that it forms, it's going to be C, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6. That's for the bromide ion. For bromine atoms, that would be the one right above it. So when it forms a minus ion, it gets an extra electron. So which element forms a +1 ion with the following electron configuration? And so 1s2, 2s2, 2p6, 3s2, 3p6. So we're talking about electron configuration of argon. And so what element would lose 1 electron and get that electron configuration? And so if potassium loses 1 electron, then it will get the electron configuration for argon. So remember, elements tend to react by losing, gaining, or sharing electrons to get noble gas configuration, because noble gas configuration is extra stable. So which element forms a +2 ion with the following electron configuration? So 1s2, 2s2, 2p6, 3s2, 3p6. So again, we're at argon. And so which element loses 2? And so if calcium loses 1, it gets potassium electron configuration. It loses 2, then it would get the electron configuration for argon. So remember that first column, they tend to form +1 ions. The second column tends to form +2 ions. So you should know the different groups of the periodic table, because again, elements in that column tend to behave alike. And so the far left, you have the alkali metals. The second column, you have the alkaline earth. You have transition metals here, noble gases all the way to the right, then the halogens, then the chalcogens, you have the lanthanides, and then you have the actinides. So you should know the different groups of the periodic table. You should also know the valence electron configuration for the different columns. So the alkali metals, they are on the farthest left. They have the valence electron configuration NS1, and so they'll have a single electron in the s orbital. They tend to form +1 cations to get noble gas configuration. They're soft and reactive metals. All alkali metals react with water exothermically to form hydroxide. And I should remind you that hydrogen is not an alkali metal. Hydrogen is not a halogen. Hydrogen is not a member of any group. And again, I mentioned that the alkali metals all react with water, forming hydroxide, and it's a very exothermic reaction. And so lithium has electron configuration 1s2, 2s1. And so the valence electron configuration is just a 2s1. Sodium has the valence electron configuration of 3s1. Now sodium, if it loses its 3s electron, then it gets the noble gas configuration of neon. Again, noble gases configuration extra stable, all full subshells, and so elements tend to gain, lose, or share electrons to get noble gas configuration. And so all alkali metals start with valence electron configuration NS1 and then tend to react by losing that, forming +1 cations. A cation is just a positive ion. Alkaline earths, they're in the second column. They have the valence electron configuration NS2. And so if they lose those 2 electrons, then they'll get noble gas configuration. And so here's magnesium. It's got the electron configuration 1s2, 2s2, 2p6, 3s2. The valence electron configuration 3s2. Now if it loses these 2, then it gets the noble gas configuration of neon. And so all alkaline earth metals have the valence electron configuration NS2, and they tend to react by losing those 2 electrons, forming 2+ cations. Chalcogens, so they're the third row from the right. They have the valence electron configuration NS2NP4. Now I mentioned that, on top you have the nonmetals, so they're going to react similarly. Now on the bottom, the tellurium and polonium, they're metalloids, and so you shouldn't expect the metalloids to act the same way as nonmetals, but they all have the same exact valence electron configuration. Now the oxygen sulfur, if they gain 2 electrons, then they'll get noble gas configuration, and gaining 2 electrons is much easier than losing 4 electrons. And so oxygen 1s2, 2s2, 2p4. Now if it gains 2 more electrons, then it'll have noble gas configuration. Sulfur has 1s2, 2s2, 2p6, 3s2, 3p4. If it gains 2, it also has noble gas configuration. And so oxygen sulfur often will gain 2 electrons to get noble gas configuration. The halogen, right next to noble gases, they have the valence electron configuration NS2NP5. And so if they gain 1 electron, they'll get noble gas configuration. So for instance, chlorine has electron configuration 1s2, 2s2, 2p6, 3s2, 3p5. And then if it gains 1 electron, that will give it a negative charge because electrons are negatively charged, and it'll give it noble gas configuration of argon. Again, noble gas configuration extra stable because all the subshells are full. And then the halogens, again, all tend to gain 1 electron, forming -1 ion. Noble gases, all their subshells are full. They are not very reactive. There are some known compounds with argon, krypton, xenon, no known compounds with helium or neon. They have the valence electron configuration NS2NP6. They have 8 valence electrons. And so an interesting question we could ask is, put the halogens in order of increasing reactivity. And so the halogens go from fluorine to acetine. Now if we think about it, they tend to react by gaining electrons. Now if we think about our periodic trends, as you go up and to the right, they're smaller, they want to grab the electrons. And so of the halogens, fluorine should be the best at gaining electrons. And so we'd expect that in general, fluorine is going to be the most reactive halogen. Now if we think about the alkali metals, which one of these is the most reactive? Now these are metals. They tend to react by losing electrons. And again, if you think about the periodic trends, as you go up and to the right, the atoms are smaller, ionization energy increases, electronegativity increases. And so the alkali metals are probably going to react by losing electrons. And so francium should be the best at losing electrons. And so in general, francium should be the most reactive halogen. And so hopefully you understand that elements in a column behave alike. They have the same valence electron configuration. Understand that noble gas configuration is extra stable, so elements tend to gain, lose, or share electrons to get noble gas configuration. Again, noble gas configuration, you have full subshells. And you should be able to use periodic trends to predict which element of each group is the most reactive in general. I hope that helps.